Welcome back. So please be informed that if I write px, pxy, py given x or py, it does not matter. Mathematically it is the same problem that I am trying to solve, just that interpretation changes. Are you all comfortable with this? You should be super comfortable with this, because sometimes I will write px, sometimes I will write px given y, sometimes I will write py given x, and so on, deliberately, because it's the problem that we are trying to solve, right? Depending upon what problem we are trying to solve, we will estimate the underlying density, right? So this, right, is, I think, let me just push it a little to my left so that it comes in the same line. See, this boxed item is what is the central problem of machine learning. It's a nomenclature again. Where is a machine here? What is learning and all that? I have not told you that, right? I mean, there's a machine which is a compute unit, right? That's all it is. But anyway, so this is the central mathematical problem that we are talking about. And as I told you, what is the main problem associated with this is that PX's the main challenge is PX is unknown, both from, or I'll write it as completely unknown. So we know nothing about PX. We have zero information about the underlying distribution, but we still want to do it. Seems like a Herculean task, right? Because if you know something about the distribution, you can perhaps think of estimating it. No, we have no information about PX. However, are we totally blind? We are not totally blind. Why? We have samples from it. So that's the central problem. So given samples from an underlying distribution, can you learn the underlying distribution? That's it. So if the problem were well defined, okay, and completely tractable, then you don't need hundreds of different algorithms to solve it. And by the way, I'll introduce another nomenclature. Every algorithm or the estimate that you get for this underlying distribution is called a model. You get an estimate for the underlying distribution, right? That's what a model is. So in large language models, the model is actually an estimator for the distribution. And I've told you, I mean, anybody who has studied the estimation theory 101 knows that all estimators are wrong by definition, and therefore all models are wrong. But some estimators are useful, and therefore some models are useful. So here is the statement: all models are wrong, some are useful, because they are density estimators. Because they are density estimators, there cannot be one correct density estimator, right? But you can compare density estimators depending upon their metrics, some metrics. Challenge is that the underlying distribution is completely unknown, and we have to get it from the samples. So this is the central question that we will be asking. So given a distribution, how do we estimate, given samples from an underlying distribution, how do we estimate its samples? So that is the central question that we are asking. So let us see how to do that. Okay, I will give you the broad framework of how to do this. Then we will see several examples of how is it done. Okay. Now let us consider. So consider we have a data set. data set D which contains which are ID drawn from an unknown underlying density Px. And by the way, this is also a sort of misnomer. This is not completely mathematically correct because we cannot you cannot sample from a density function. You can only sample from distribution functions. But yeah, so I will make that leap of faith and write it. Okay, so sampling ID from an unknown density, and this is what we are starting from, right? The goal is to estimate the underlying density. Okay, now any estimation problem. Remember in the very first class, I talked about a function approximation problem, right? You have x and y, which are samples from two given sets, and we are learning a function between those two sets, and all we have are samples from that. We don't know anything about the function. So what has been the historical method to do it? Historical method to do it is that you start by making some assumption on the unknown function and then try to solve an optimization problem. That's what I told you how to do it. Because if you are totally blind, you can't do anything. You have to start with some stick or something, right? Totally blind is completely lost. Now mathematically speaking, the way to do it is assume a functional form on Px. You assume a functional form on Px, or better way to say it is assume a parametric functional form on Px, okay, denoted by p theta. We are estimating the underlying density function, okay. We don't know anything about it. What we say is that let me assume that my underlying density comes from a parametric family of functions, call it p theta. Please remember, what are we trying to estimate? Remember that we are trying to estimate a function from the range space of the random variable 2r plus by definition. This is what we are trying to estimate, okay, and we assume that this function has a particular parametric form p theta. So what do you mean by a parametric function? A parametric function is a mathematical function object that has a few parameters. One example can be a line. So let me give examples, right? Example can be, so p theta 1, or what do I call it, pa is of x, because it is on x, can be running out of alphabets, I told you. So let's say this is w1 times, so x is a vector, so let's say that x is in Rd. If it's in Rd, then this is w1 transpose time x plus w2, where w1 and w2 are also in Rd, right? So here theta is w1 and w2. This is one example. Now I can, so this is one example that I can take for w1 and the parametric family. The other example can be that I assume this to be a Gaussian distribution, right, with this particular density function, and this can be, so this is this n represents that I am looking at. I am assuming that all of you know, okay, maybe just for sake of completeness I will tell you. See, when we talk of density functions, there are a few well established standard density functions. So examples can be a Gaussian density function, right, and an exponential random variable density function, or if you look at discrete random variables, then you have the Bernoulli random variable, and so on, right. We will look at a few examples later. These are some standard examples of density functions. So you can take them, you can take those to be your choice for your functional form. So it can be a Gaussian distribution which has parameters mu and sigma, okay. In this case your theta is the set of mu and sigma, right, mu is another vector in Rd, and sigma is a vector in R d by d. Correct? This is a Gaussian distribution and so on. So I mean, see, this is your model choice. You have to choose a model, and we will see 10 different examples for this p theta in this course. Okay, we will also study why one model is better than the other and so on, right? What advantages can it offer and so on. And the so called neural network or deep neural network is one such example for this p theta. We will see what sort of examples we can take. So that is the design choice. So given a problem, so what you are actually given is this, right? You are given n samples from an unknown distribution, and you want to estimate the underlying distribution. What you do is you start by making an assumption on p theta, and that is your model choice. You choose a linear regression, or you choose a logistic regression, you choose a neural network, you choose a kernel machine, you choose a GMM, you choose a transformer. All of these are p theta choices for this p theta. That is it. Make sense? We will see multiple models in this course, and that's each model. Okay, so you make an assumption. So then once you do this, now you have already fixed a particular model. Okay, the degree of freedom is already lost. How? You are making a big leap of faith that the underlying density function actually has this functional form. So somebody asked a question 10 minutes back. How do we know whether that is the particular density function, that density functional family that my density function belongs to? We will definitely not know. However, thankfully, we have a few functional forms that are known to be universal function approximators, in the sense that if you choose the parameters of those functions properly, then they can approximate any function to arbitrary closeness. Mixture densities are one such family, which we will see later, and neural networks are one such family. That is why today the go-to choice for this p theta is a neural network, because the neural networks are families of functions that can approximate any function to arbitrary closeness. That is called universal function approximation capability. That is why you choose such models in practice. However, once you choose a model p theta, you are making this big leap of faith that my underlying density function is a member of this family. For instance, if I choose my underlying model family or p theta to be this particular form, this is called the linear model. If I choose it to be this form, then I am saying that my density function can be represented as a hyperplane or a line. It is not a line, because a line is in one dimension, it is a hyperplane in 3 dimensions. You assume that it is a line that my density function is. Now what if your density function is actually a quadratic function? You are lost. It's a very bad model. I told all models are wrong. This is a very wrong model, or rather a worse model. But you are stuck with it. The moment you make a choice for p theta, the algorithm will not take care of the model. It will only take care of, given that I have made an assumption that my reality or the underlying density function is a line, tell me what line it is. That is an algorithm. Okay. So how many lines can exist in practice in RD, or rather in theory in RD? Infinite line can exist, because every line is separated by these two parameters, right? The intercept and the slope. If you change the intercept and slope, you will have a different line. So once you do this, so assume this is a recipe, okay? The recipe to solve an ML problem is the following, right? The first step is assume a parametric functional form on Px denoted by p theta. This is the first step. So this is your model choice. This is also called the model choice. Make a model choice, or choose a model. Okay. Once you do this, what do you do? Chosen a model. The next step is, what do you mean by that? Mathematically, I have not even talked about an algorithm. I am abstracting things out even at one level higher. Okay. The next thing to do is define or compute a distance metric between, not define actually, you actually have to compute a distance metric between Px and p theta. See, what is the problem that we are solving right now? We have assumed that my underlying density has a particular functional form. the question that we are asking next, the next logical question to ask is, given that my density function is a normal density, tell me which normal density it is, because there can exist infinite normal densities, right? If you change the mean and the variance of a normal density, you will get a different normal density. Now, having fixed that my underlying density function is a normal density, the next logical question that I will be asking is, amongst infinite possibilities for this normal density, tell me which normal density should I choose. To do that, I need a notion, okay, of how good or bad a particular choice of normal density is. Suppose I choose my normal density. What do you mean by choosing a normal density? Fixing the mean and variance of the normal density, or this theta, right? These are called parameters. Let me write that. So, this theta are typically referred to as parameters. So, if you fix a particular value to this parameter, you will get a different model. Now, suppose you fix a particular value to this parameter, you will get a model. Now, I need a way to tell you how good or bad a particular choice of this p theta is. How do we do it mathematically? If there were a way to quantify the distance between density metrics, the larger the distance is, the poorer the model is, correct? So, first we need a way to define a distance metric between the true density that we are trying to estimate and the model choice that we have made. That is what we need to do. So, let us call that as I was supposed to use capital D for this now. Again, I have used D already for data sets. Let me use small d. So, let D denote the distance metric between Px and P theta. Did you notice that I wrote distance metric within quotes? Because the metrics that we will be using in practice are not metrics, in the sense that a distance metric has to have a few properties such as being symmetric and obey the triangular law of inequality and all that. The metrics that are used currently in machine learning do not have those properties, and therefore they are not metrics. Some notion of divergence, or rather distance between distributions, that is why I put this thing within quotes. They are not metrics mathematically speaking, right. So, it is a function. What is that? It is a function d which takes Px and P theta as inputs, okay, and maps it to some positive real number, right. So, it is a function that takes two distributions as input, you see. So, it is the cross product of two distributions that it takes as input and maps it to positive real numbers, because we need the notion of distance, right. It cannot be negative, it should always be non-negative. So, therefore, this is the kind of function that we define, okay, fine. Let us say that we define this and there is a way to compute most of the ML algorithms, right. So, this is easy. Making a model choice is very easy. Why? Because you just choose a function, okay. The algorithmic difficulty, okay, comes in the subsequent steps. The second step is to define this distance metric. Now, this definition is also easy. Just like you choose a model, you choose a distance metric between them. And by the way, what differentiates one ML algorithm from the other is the choice of this function, obviously, and the choice of this metric also. In fact, there is the third, in the recipe we have the third step where we find the parameters by solving an optimization problem. The algorithm that is used to solve that optimization problem is also what differentiates one ML algorithm by the other. So, I give you the recipes, ingredients, now put one here, one there, you get one different ML algorithm. That is what we will see several examples of this, several algorithms in this course, but this is the general recipe, right. So, choosing a distance metric is not difficult. In fact, what is difficult is to compute this distance metric, because we are sort of begging the problem if you look at it. We started by saying that we do not know Px, right, but the distance metric that we defined will take Px as an input. Now, aren't we begging the problem? Aren't we coming back to the step 1? Because we started by saying we don't know Px. Now, we need Px to compute P theta. Turns out no. So, there are statistical methods where you can compute. See, this is where things like a law of large numbers and the other probability theory ideas that you studied comes handy. We will see that as we move on in the course. So, they are not mere useless mathematical constructs. They are constructed for a reason, and we will see the usage. So now, yeah, hold on, let me complete. So now we have to compute the distance metric. Assume that we will come up with algorithms to compute it. So we need a distance metric. So now what have we done? We have chosen a model. We have a distance metric, assuming and we know that we can compute it. So now, given a model, it will tell you whether how far or close this model is to reality is. Fine. What is the third step? The final step is, I will complete this and then take your question. The final step is, find or estimate theta, estimate the parameters theta by solving the following optimization problem. What optimization problem we will solve? We will seek a theta, which I call theta star, the optimal parameters, such that the distance metric that I have defined between Px and P theta is minimized. And you know what this is referred to as in ML community? This is called training. Training the model. Okay, I want to write that, I can write that. See, this course won't teach you anything different than what is already there, but I will tell you the story from a completely different angle, which is so broad that you can encompass 100 other different stories within this framework. That is the objective of this course. So, everybody knew that models will be trained in ML, right? But yeah, so this is the framework that we construct here. Okay, so that's all it is. So how do we do? Now our problem boiled down to, given D, solve this optimization problem. And I am assuming that all of you know this notation. I will be using this notation multiple times. Argmin, for the benefit of the online audience, I will just define it. See, argmin is the argmin, yeah, not yeah. Argument minimum. So if I write argmin of a particular function, the question that I am asking is, suppose I minimize this particular function, okay, with respect to this parameter theta, at what point in theta space does this function achieve its minima? The argument at which the function attains minima. It is not the minimum value of the function that I am seeking. I am seeking the minimizer, or the argument of the function that minimizes this function. Oh, I will be writing this. So that is the recipe. Let us walk through it. This is the entire recipe of what we will be doing in this complete course. We will be seeing 10 different methods of doing this. Okay. The input is that we are given some data set D, okay, which contains samples that are drawn from an unknown distribution, and our interest is to estimate either the distribution or some surrogate of it, depending upon what the problem is. What is the recipe that we use is that we start from assuming a parametric functional form of the underlying distribution that we are trying to estimate, okay, and then define and compute a distance metric between the true distribution and the assumed model distribution, and find the parameters of that model by solving the optimization problem that would seek the minimizer of the distance metric between the true distribution and the model distribution. That is ML for you. Okay. So what we will be doing in this course right now is, we will ask questions like, what model, what choice of P theta should we take, okay, what is the choice of distance metric that we should be looking at, and how do we solve this optimization problem. It is non-trivial because most of the distance metrics are non-convex. So you cannot use any of the well-known optimization techniques to solve this. You will be surprised to know in today's time and age, the go-to standard choice for p theta is a neural network. Okay, and the go-to choice for this optimization problem is first order gradient descent. For all optimization that we have studied in our previous courses, all the conjugate gradient methods and second order methods and so on, world to ML is artificial general intelligence is being achieved by using a simple first order gradient descent. Yeah, so that's all. So we'll see that in the course later. So we'll solve these optimization problems using the numerical gradient descent method of the first order, and the typical amount of parameters that are there in today's models, like like GPTs and so on, is of order of billions. We are, please appreciate this scale. We are solving an optimization problem in a billion dimensional space, because number of parameters are billion. Of course, we will not start the course with billion parameters, we will start with 5-6 parameters and so on. Now, the current scale is that of billion parameters. So this reminds me of an anecdote that happened when I was in Delhi. Right in front of IIT Delhi, there is this institution called Indian Statistical Institute, ISI. Okay, a lot of economists and statisticians and so on. So I was having a conversation with an economist once, and they were saying, yeah, I mean our models. I'm trying a larger model for a problem that he wanted to solve. He's saying I'm trying a very large model, and see, a larger model is not a good model, right? Because you don't need too many parameters in your model. You need lesser number of parameters. He was telling me that, oh, I'm using a larger model now, and I want to reduce the number of parameters and so on. Curiously, I asked him, how many parameters does your model has? He says, oh, it has gone to 8 now. I have 8 parameters in my model. I said, what? 8? So we are talking about 8 billion parameters, right? So that's the scale. So initially, all the linear models, etc., they were talking about 10 parameters, 15 parameters. If your data is in 100 dimensions, then you have the linear model will have 100 parameters, 100 plus 100, 100 for slope and 100 for intercept, 200 parameter model. Today's models have billion parameters. But what's the most interesting and satisfying thing is that no matter how the models have changed and the landscape has changed in terms of scale, the underlying mathematical problem that is being solved remains the same, and this is the problem that is being solved. The problem that we are after is that, see, this px that we are tackling right now is the amalgamation of all human knowledge that has been seen in history. That's AGI. So imagine that the random experiment that we are considering and the sample space that we are considering is the entire universe, and all documents, all text, all images, all kinds of data that has been produced in the entirety of human race is what are sample spaces. And we are assuming that there exists an underlying distribution, and throwing our machinery with a lot of scale and too much compute and data comes out AGI. Why is still an open question. So is this the only way to crack human intelligence? Perhaps not, and most likely not, because a child does not need this much of data and this much of compute to learn. We are also learning an underlying distribution. Even human learning can be cast as this problem. There is, every time we make a mistake, we get a feedback, and then we go back and so on, right? Maybe we are estimating distributions, but we don't look at the amount of data that today's models look at, right? And the power consumption that our brain has is orders of magnitude lesser than what today's models take. So maybe there is a parallel model for intelligence. Yeah, that's for some other day's discussion, but this is the recipe, okay? And we will be looking at several ways of solving this problem. Choose different models, choose different distance matrices, choose different optimization algorithms, and that makes, if you choose, I'll tell you, right? If you make this p theta to be a linear model, and you make this to be the Kullback-Leibler divergence, and you solve this optimization problem in a deterministic way, then it becomes a linear regression. If you make it compositions of sigmoids, and if you make this distance metric again Kullback-Leibler divergence, and you solve this using numerical gradient descent using a repeated application of chain rule, which is called backpropagation, then this becomes a deep neural network and so on, right? If you use the dual methods of optimization under a kernel method formulation, then that becomes a support vector machine and so on. We will see all this, don't worry about these terms, these are jargons. So basic idea is that you make a choice for p theta, you make a choice for resistance metric, you solve the optimization problem, and that's your ML. Okay. Any questions on the formulation? Yeah. That's a question that we will answer. The question is, when I told you, right, we are beginning the question. Since we do not know Px, how do we calculate the distance metric? That is what we will see next. Statistics help you there. Your probability theory the probability theory course will help you do that. Okay.
Core domain of this distance matrix should also include
R plus.
0, no?
R plus includes 0.
So we jump from a place where we were trying to estimate the distribution to a density function. How does it change the scale? Let's say.
Yeah, the question is, we jump from solving or estimating distribution functions to density functions. Does it change anything? Does it change the scale, etc., or anything? No, it does not, because the density function and distribution function, in the cases where they are both defined, have a one-to-one relationship, right? So we work with density functions. That's it. That's for mathematical convenience. See, for instance, Gaussian density is easy to compute and so on. Or Gaussian distribution is a little difficult. That's where you need Q functions and so on. Remember those tables and all that. Density functions are easy to work with. That's the only reason we work with density functions. Okay. Okay. See, before we move on with this, there is one detour that I want to take. Okay, and not written that thankfully. A detour that I want to take is that in the first class, I told you that there is a deterministic way or non-probabilistic way of looking at machine learning, correct? Right? Where you have, see, even there the starting point is the same. You have X and you have Y and you want to learn a mapping. Now, I cannot talk about unsupervised learning in that framework. Now, you see why it is so difficult to stick to non-probabilistic ways. Okay, but anyway, so let's say that you have X and Y and you want to learn a function and you make an assumption on that function and still solve an optimization problem, right? That's what you do there as well. Now, does that, assuming that this X and Y are vectors from some space, which is Rd and Rk, and all you need to learn is a function between those two, assuming that there exists some function. Now, we have this worldview that those X and Y's are actually the range spaces of two random variables, right? Suppose we give up that worldview and say that, okay, these are two sets and we want to learn a function between these two, and there is some framework which is called risk minimization framework or function learning framework. Something comes up. The question is that something which comes up, how does it connect to whatever we have seen? It turns out that they are exactly the same thing. So I want to show you that. Okay. The framework of empirical risk minimization or risk minimization, which is what is taught in an ML 101 class. I want to show that empirical risk minimization is exactly the same of distribution estimation and getting the parameters of the distribution in this framework that we just saw. I want to show equivalence between those two, because when we move on, right, when you read a textbook, for instance, some textbooks choose to stick to the non-probabilistic way of looking at things. So for instance, there is this textbook by Christopher Bishop, right, pattern recognition neural networks. The treatment is mostly non-probabilistic, but there is this book by Kevin Murphy. The title of the text itself is Probabilistic Machine Learning. Okay, so there both treatments are seen in the literature. I want to sort of first fix the equivalence between those two, so that when we move on, you know that we are doing the same thing. Okay, so we will do that in the next class. So when we come to the next class, yeah, thanks for attending this class. So this ends this particular class. So just recalling, right, we formally today defined what the problem of machine learning is. So the problem of machine learning is that we are given a few samples that are drawn IID from an unknown underlying distribution, and we want to estimate either the distribution or some of the surrogates of it. That's the entire problem, and the challenge with the problem is that you don't know the underlying distribution. So the way to do it, the general recipe is that you start by assuming that the underlying distribution has a parametric form, and define and compute a distance metric between the true distribution and the model distribution or the parametric functional form and solve an optimization problem. It always happens that when I summarize the class for a day, it looks like why did I spend 90 minutes on this topic? Always happens that way. But anyway, so that's for today. And when we come to the next class, as I said, I will start from the risk minimization framework and I'll show you how risk minimization framework is exactly the same as this, and then we start by looking at the linear family of models. Okay. Thank you for attending this class.